Okay, so this is meant to be a short talk slash lecture to introduce profinite groups, meant for the residual and finite methods session in at the NCNGT conference. Yeah, so I hope that this can just bring everybody up to speed on what a profinite group is, what the profinite completion of a group is, and what it means for a group to be profinitely rigid, because I think those will be central concepts in the conference. Okay, so let's jump right in. So a topological space is called profinite if it is the inverse limit of finite spaces. And yeah, each of the finite spaces will have the discrete topology. So I've used blue to denote a word that I haven't defined yet, and red is always the word that I am defining. Okay, so I've defined what it means for a space to be profinite, but we need to say what it means for a space to be the inverse limit of something. Okay, so that brings us to our next definition, which is a bit technical. First, you have to start with a poset I, or a partially ordered set I, where less than or equals here denotes the order relation on I. And then a collection of X objects, Xi. And the objects really, it's quite general. So the objects can be sets, they can be topological spaces, groups, rings, but I mean, most of the sort of natural objects that you come across, you can make this definition for. Okay, so you have your poset, you have your collection of objects indexed by the poset, and then you want that whenever I is less than or equal to j in the poset, there should be a function. Okay, so here I've said function if you're in the category of sets, but maybe a continuous map if you're in the category of topological spaces. If you're in the category of groups, then group homomorphisms, rings, ring homomorphisms, and so on. Okay, so whenever I is less than or equal to j, there should be some map in the category going from xj to xi, and we denote that map fij. The next thing we want is some compatibility between this big collection of maps that we have. Namely, we want that when you compose two maps, so fjk then compose with fij, of course, whenever that makes sense. So I needs to be less than j, less than k. Okay, you get fik. Yeah, well, I mean that's the condition. You want this composition to give you fik, this map going from xk to xi. And I've forgotten to write something else, which is that you also impose that fi should just be the. Oh, maybe I'll write. This should, of course, just be the identity map on xi. And this is for all I in the poset. Okay, so all of this data together is called an inverse system, or a directed system. Yeah, this is what I've written here. And the inverse limit of the directed system is this object here. I'll give an example in a second to make it a bit clearer, but the point is the inverse limit denoted lim inverse of I of the xi's is, okay, so it's a subset of the product of all the xi's. And then you ask for, in some vector x in this product, you need that the ith component is the image of the jth component under the map fij whenever I is less than or equal to j. So it's like a compatible choice of elements from all the xi's. That gives you a single element of the inverse limit. Okay, so now we can go back to the definition of a profinite space. You're a profinite space if you are the inverse limit of finite spaces, where you have some big directed system of finite spaces, all of them with a discrete topology, and you take the inverse limit and you get some space x, which is the inverse limit. And of course, the way to topologize this limit is just giving it the subspace topology of the product. Okay. So here's an example to maybe make this a bit clearer. So we have a simple directed system here, where each of the map is just the mod 5 to the I reduction. So here you're going from Z mod 25 to Z5 just by reduction mod 5. Here from Z125 to Z mod 25, again, reduction mod 25. And what we're hiding in the inverse system is, of course, there are all the compositions. They're also there. But if we were to write that for every single map, all the compositions, it would just get a bit crazy. So we just kind of keep it to a bare minimum and denote the whole directed system like this. Okay, so now what are some elements of the inverse limit of this directed system? Well, 1, 1, 1 forever, 1, 1, 1, 1, 1. That is a valid element. Let's say it is an element of the inverse system because 1 always projects to 1 under reduction mod anything. So there's almost just nothing to check there. And I mean, n for the same reason forever in all the components. That will also be an element of the inverse limit. A less trivial element is this one here, where I've written only the first 3 components. So 1, 6, 81. So 6 projects to 1. So the 6 is really an element of Z mod 5 squared. And here this is really should be viewed as an element of Z mod 5. And 6 does project to 1 when you reduce mod 5. And similarly, 81, which is now an element of Z mod 125, projects to 6 when reducing mod 25. So this so far has been a compatible choice, and yeah, you have to extend it forever. But yeah, I think this gives the idea of what it means to take a compatible choice, at least in this setting. And okay, so here's an element that's not an element of it's an element of the product, but it's not an element of the inverse limit. So 1, 2, 3, 4, I mean, these are just not compatible. 2 doesn't project to 1, 3 doesn't project to 2. None of them really projects to any of the others. I mean, not quite, but yeah, that's the idea. Okay, and yeah, just as a side note, this inverse limit is the ring of 5 adic integers. That's just one definition. And I mean, you can define the p-adic integers in this way as well. Just replace 5 with your favorite prime key. Okay, so yeah, another definition. So I want to get to the definition of a profinite group. So before that, I need to define a topological group. So yeah, a topological group is a group with a topology that makes the multiplication and inversion maps continuous. Yeah, I've written that down here. So examples of that are S1, which is a group. So S1 can be defined as all of the norm 1 elements of the complex plane. And you can check that pretty easily, that multiplication and inversion are continuous functions here with respect to the normal topology on C. And okay, R with just the additive structure, this is also a topological group. The inversion and multiplication are obviously continuous maps here. Okay, and then we can get to our definition. So G is a profinite group if, okay, it's both it's a topological group and it's also profinite as a topological space. So we have our definition of a profinite topological space. We have a topological group. So if all these things are compatible, then we get a profinite group. Okay, so we don't really have many examples yet of profinite groups, but I mean, every finite group is a profinite group. It is the inverse limit of the directed system containing only itself with a discrete topology. So that's a trivial example of a profinite group. Okay. So a more interesting way of making profinite groups, which will appear a lot in the conference, is via the profinite completion. So I want to explain how to do this now. So this is definition / construction. Yeah. So for any group, just an abstract group, you always have this directed system. So I call it here the directed system of finite quotients. So the elements of the directed system are finite quotients of the group. So G mod n, whenever n is a normal subgroup of G of finite index. And then this is, you want the order, I guess. Or I think I'm going to get confused if I try to figure out which way the order should go. But the point is that the maps that go between the elements of the directed system are just reduction maps. So this is just reduction mod n1 here. So whenever n0 is a subgroup of n1, there is a reduction. I can just quotient further. So I quotient this group G mod n0 by n1, and I get, or the image of n1, I should say, I get G mod n1. Yeah, so this defines a direct system, and you can just define the profinite completion of G to be the inverse limit of this directed system. So now, before saying anything, I should just say G is profinite by construction. All of these groups, G mod n, you give them the discrete topology, and you topologize G hat with the topology on the directed, just the induced topology on the inverse limit, and you get a topological group G hat, and it's profinite because it's the inverse limit of these finite discrete topological spaces, or discrete topological groups. Okay, so this gives us a lot of profinite groups. I mean, we don't really know what they look like at all yet. And this construction is not going to be interesting for every group, because, for example, if G is a simple group, it's not going to have any finite quotients other than the trivial group. So the profinite completion of a simple group is just going to be, of a simple infinite group, I should say, is going to be, I need to add this to simple and infinite. So if you take an infinite simple group, then its profinite completion is trivial. If you take a finite simple group, then the profinite completion is obviously just itself, but that's the same for any finite group. Okay, so I meant to leave this on as an example, but it was an exercise. So in this setting, we do get interesting examples of profinite completions, at least in some sense. So the statement here of the exercise, the statement to prove, is that there's always this canonical map from G to G hat, which sends an element G to the just the element G, G, G in each component, and this is obviously a valid element of the inverse limit of the profinite completion. So the statement is really saying that this canonical map is an inclusion. So this is the part that is emphasized here. If and only if G is a residually finite group. So just a reminder, or a definition if you haven't seen this yet. So a group is residually finite if whenever you take a non-trivial element of the group, there is a finite group Q and a homomorphism F from the group to Q, such that F doesn't send G to the identity. It doesn't kill G. So this is sort of saying that every non-trivial element of the group is seen in some finite quotient of the group. Being residually finite is useful, for example, for algorithmic properties of groups, because you can being able to see things in finite groups is obviously very useful if you want to decide things algorithmically in a group. I won't say, yeah, I'm not going to say anything more about that. Okay, so yeah, for this reason, for the reason given in the exercise, we usually restrict ourselves to finitely generated. I mean, the finitely generated is because we always restrict ourselves, at least in GGT, to finitely generated groups. But yeah, the important thing is really we're restricting ourselves to residually finite groups. Yeah, when you're dealing with residually finite groups, taking a profinite completion doesn't really destroy any information in the group. So if you want to study things about a group from its profinite completion, really it makes sense to study that for a residually finite group. Because if you're not residually finite group, you know that when you take the profinite completion, you are going to destroy some information in the group. This isn't, yeah, I mean, this list here that I give is to say that it's not really a huge restriction. Lots of the groups that we sort of see in nature are residually finite. So, I mean, finite groups are obviously residually finite. Free groups are residually finite. Finitely generated abelian groups are as well. Surface groups are residually finite. Three manifold groups are residually finite. So this isn't sort of in roughly increasing order of non-triviality to show these things. Yeah, I would say, you know, three manifolds. It's a theorem. It's hard to show, but surface groups is also already quite tricky to prove that they're residually finite. But I would leave definitely, I mean, free and finitely generated abelian groups as good examples, as good exercises. I mean, okay, yeah, I mean, many other groups, of course, are residually finite. Okay, now we can define what it means for a group to be profinitely rigid. So yeah, there's a lot on the definition here. First, try to just ignore all of the blue stuff in the definition. I'll say what I mean by that afterwards. So a finitely generated residually finite group G is profinitely rigid, or sometimes to emphasize, it'll make more sense after when I talk about the blue stuff, is absolutely profinitely rigid if G hat, so the profinite completion, is isomorphic to H hat, so H is some other group. I'm going to say what it is in a sec. And here, this is really like isomorphic as topological groups. So there's a group isomorphism that's also a homeomorphism. Okay, so whenever the profinite completions are isomorphic, that should imply that the group G was isomorphic to the group H. And here you put again this restriction that H is another finitely generated residually finite group. So the point is that you're never profinitely isomorphic to G unless you were G to start with. So you don't get sort of random, well, not random, but you don't get some different group who has the same profinite completion as G, but is not isomorphic to G. So proving that groups are absolutely profinitely rigid is usually very, very hard. So it often makes sense to restrict ourselves to some smaller class of groups than the class of all finitely generated residually finite groups. So, okay, this is where the blue comes in. So let's let C be some class of residually finite groups. And now assume that G is in C. So now the absolutely part goes away, but we say that some group G in C is profinitely rigid within the class C if, again, the same thing happens. So whenever G hat was isomorphic to H hat, that was only because G was isomorphic to H in the first place. And then here you ask that H is finitely generated residually finite, but also was in C to start with. So restricting yourself to a subclass of residually finite groups is often the only way to really say much about profinite rigidity. I mean, that's not to say that, I mean, there are lots of highly non-trivial theorems about, I mean, we'll see some later, about this like relative profinite rigidity. But yeah, yeah, it's usually, I guess it's the only way to really make any progress. Okay. Now a theorem that I want to state before giving an example of an absolutely profinitely rigid group is this theorem of Dixon, Formanek, Poland, and Rebus from 1980. And it says that if G and H are finitely generated, not necessarily residually finite, then the profinite completions of G and H are isomorphic if and only if the isomorphism classes of finite quotients of G and H are equal as sets, which is really quite surprising. I think because you would expect, the profinite completion has a lot of structures, the inverse limit, and somehow it encodes all these quotient maps. And the set of all finite quotients, or really to be more precise, the set of isomorphism classes of all finite quotients, is kind of just a big bag of finite groups. I mean, it's all the finite quotients of the group, but it doesn't record any of the maps going between them. So somehow you feel like you've lost a lot of structure. But I mean, yeah, this theorem says that you actually haven't. So if you know that the two set of isomorphism classes of finite quotients of two groups are the same, that is exactly the same thing as them being profinitely isomorphic. Okay, so asking about profinite properties of a group or whether two groups are profinitely isomorphic is really just the same thing as asking about their finite quotients, and I mean their set of finite quotients, really. Okay, and now let's use this theorem to prove that Z is absolutely profinitely rigid. So this is the absolute sense. Okay. And this is really, I think, the only easy example of apart from, okay, you can do the same thing for finally generated abelian groups. I'll leave that as an exercise. But these are the only, I think, easy examples of infinite groups that are profinitely rigid. Okay, so let's let H be some finally generated residually finite group that is profinitely isomorphic to H, so it has the same profinite completion. So the first claim is that H is abelian. So let's show that. Suppose it is not. Then that means that there are two elements of H, H1 and H2, that do not commute. That means that their commutator H1, H2, this commutator here is not the identity element. Now we're assuming that H is residually finite, so that means that there's a finite quotient of H where the commutator doesn't die. There's a finite image. So yeah, there's a finite image of H where the commutator is not the identity, and that means that this finite image is non-abelian. Okay, so H has a non-abelian finite quotient, but Z has no non-abelian quotients. We're assuming that the two groups are profinitely isomorphic, so by the previous theorem, they should have the same set of finite quotients. But this is a contradiction to that. One has a non-abelian quotient, and Z only has abelian quotients. Okay, so from step one, we have that H is abelian, and now step two, let's just show that it's isomorphic to Z. So first, let's assume that H is not cyclic. We already know that it's finitely generated abelian. So from the classification theorem for finitely generated abelian groups, it's pretty easy to see that H has some quotient of the form Z mod P times Z mod P, which is, this is not cyclic. So really the point is that H has a non-cyclic quotient if it's not cyclic, and it's finitely generated abelian. But I mean, Z is cyclic. So, I mean, it has no non-cyclic quotients. All of its quotients are cyclic. Again, we use the previous theorem to say, okay, well, H had a non-cyclic quotient. but G had a cyclic quotient. That can't be the case because they're profinitely isomorphic. So you conclude that either H is finite or infinite, in which case it's Z. Now, obviously, H can't be finite because, I mean, if it was finite, its profinite completion would just be Z mod M, and Z hat is infinite, so that can't happen. So you conclude that H was actually isomorphic to Z, and that concludes the proof. Okay. So I'm gonna end with just some theorems, some recent theorems in profinite rigidity, some of them by some of the speakers of the conference. So the first one I want to mention is this result of Bridson, McReynolds, Reed, and Spittler, who proved that there are fundamental groups of hyperbolic three manifolds that are absolutely profinitely rigid. So they're really profinitely rigid among all finitely generated residually finite groups. So this was a really big breakthrough. And Tam, Cheatham, West proved that you can actually also produce fibered examples. So closed hyperbolic three manifolds that are fibered, which means, I mean, manifold is fibered if it has a map onto the circle, well, a fibration onto the circle, I guess. So or another way to say it is that it's a mapping torus of a surface. So yeah, he proved that you can also find these examples of fibered closed hyperbolic three manifolds whose fundamental groups are absolutely profinitely rigid. And again, I mean, I just want to maybe emphasize that we're using this non-trivial fact that three manifold groups are residually finite for this to even make sense. Okay, next. So fundamental groups, this is another really nice result of Yi Liu from 2022. And he proved that the fundamental group of finite volume hyperbolic three manifolds are almost profinitely rigid. And okay, maybe before I say this, I'll just say what almost means. That means that if let me write it down. So I mean, yeah, like if G is some, yeah, pi1 of a hyperbolic three manifold finite volume, but I won't write it. Then there exists finitely many. So this is what the almost means. H that are also pi1 of hyperbolic three manifolds, such that G hat is isomorphic to H hat. So it's not quite profinite rigidity, even in the class of hyperbolic three manifold groups. But it is sort of the next best thing, which is that there are at most finitely many other hyperbolic three manifold groups whose profinite completions are isomorphic to the one you started with. And the last result that I'll mention, which will be spoken about at the conference, is this theorem of Hughes and Kudlinska, recent results, who proved an analog of this Liu result for generic, I don't want to say what that means, three bicyclic groups. So they have some almost profinite rigidity statement for most, in some sense, three bicyclic groups. Yeah, and I think I'll stop there. So thanks.